What is up, everyone? Hello, how we doing today? Today we're going to be doing some physics FRQs. I'm gonna be doing 2024 today and 2023 today as well. I have 3 hours until that I know. I have three full hours. Um, till I know. What do I say? I have 3 hours until I think might have to go. But we're gonna try to see as much as we can get done today. So yeah, we're gonna be doing 2024 today, 2023. It's currently 11:51 a.m. I have an hour and a half to do an FRQ. We're trying to speed run this one and try to see how many we can get done. Shoot, man, I might get all of them wrong, but we'll see. Okay, let's just get started off. Okay, so this is 2024. Number one, question section 2. Time hour and a half. Let me see if I can whatever. Okay. So we have this ball looking thing going down, going to loop to loop. Okay, this is probably better. Probably better view angle. Okay. Block M, mass M, released from point of rest, a height of 6r above the horizontal. During release, the block slides on the track as shown. When released from point A, the block does not lose contact with the track at any point. Points B and C are located at the highest points of the respective circular loops. Both of our radius r. All frictional forces are negligible. Okay, sweet. So we have this block. It starts at 6r right up here. It's gonna go down. It's gonna go do a loop to loop at this smaller thing right here. Loop to loop, gonna go up, and then do loop to loop here. Go over here. This has 2r. This radius is r. This radius is also r. And then we have 3 points A, B, and C. Okay, let's keep on going. We do an energy bar diagram. Okay, here we go. Diagram A shows an energy bar chart that represents the gravitational potential energy UG of the block Earth system and the kinetic energy. And the kinetic energy K of the block at point A when the block is released from rest at a height 6r. Draw shaded regions of diagram B that represents the gravitational potential energy UG and the kinetic energy of the block Earth system when block is released from point B, a height of 2r above the horizontal. Okay, so we have a diagram A at point A and diagram B. So this is gonna be 1, 2, 3, 4, 5, 6. So the gravitational potential energy is gonna be 6 lines. So I can correlate that to 6r. Diagram B, so that's gonna be a height of 2r right here. And then this is gonna be 2r here, and then it has to add up to 6, so I have to do 4. Alright, so here we go. Should I record this as well? Oh, I'm not gonna record it. Okay, whatever. Maybe I'll record another one. Starting with the energy conservation energy derived expression for the speed of the block at point B. Express your answers in terms of r and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the. Okay, so I'm gonna start with conservation energy. I have UG over here from point A, and from point B I have UG and K as well. So I have UG, UG plus K. UG is also going to be known as MGH. UG here is MGH, and K is also kinetic energy, which is going to be 1/2 mv squared. And MGH height is the height of this block at point A is going to be 6r. I can just write that in. I can substitute that in. So mg6r equals mg. This is the height at point B, which is going to be 2r. Looks like 2r plus 1/2 mv squared. And notice how I'm being asked for the speed of the block at point B. So in the end, I'm going to be solving for this v right here. Okay, I can just automatically cancel out m because every term has that one. And then I'm gonna isolate the 1/2 mv squared. So I'm gonna have g 4r equals 1/2 v squared. Take the 1/2 to the side. 8 gr, and v is gonna be equal to radical 8 gr. Okay, sweet. Here we go. That's gonna be our final answer right there. Okay, on the following dot that represents the block, draw and label the forces, not components, that are exerted on the block at the instant block slides through point C. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Okay, so at point C, here we are, right? The block is going to be up here. The point is right here. So it's obviously going to be having it's going to be having a downwards gravitational pull because we're in the Earth. So FG right there. And then also the track is going to exert a normal force as well. Just as so. Normal force as well. So I get points for drawing a downward arrow. I get another point for drawing another arrow for normal force. There is no penalty for showing. There's no penalty for showing like the magnitude of these. This is arrows of any non-zero magnitude can earn these points. So as long as it just shows a magnitude of any sort, I'll get the point. Whether the FG arrow is greater than the F normal force arrow, that doesn't matter. They can be equal. They don't have to be equal. I mean, that doesn't really. You really can't tell you. They're just telling you to write some, draw some arrows really. Student claims that 4r is the minimum height at point A, such that the block can slide through point C without losing contact with the track after the block is being released from rest. Briefly explain why this claim is incorrect. Okay, so basically, the person is saying if I release the block from a height of 4r from up here, if I release block A from here, and I let it slide down, and I go over here, then that is the minimum height it needs to have in order for it to go through point C, right there. Well, my friends, that is incorrect, and I have to disprove that. And how am I going to disprove that? Well, here we go. Essentially, if I start out with an energy, an mgh, of gravitational potential energy of 4r, of mg4r, right? This is going to be gravitational potential energy, and I have that at 4r, so mg, 4r. That means that's all the energy I have in the system at the moment. It's gonna be released, go down the loop, and it's gonna go to a height of 4r at point C, right? So at point C, it's gonna be at a height of 4r. So at point C is also gonna have a gravitational potential energy of mgh or mg4r. Well, my friends, if all the gravitational potential energy is gonna go and be converted to gravitational potential energy at another point as well, it doesn't have any more energy to be converted to kinetic energy. So therefore, there is no way that block is going to have any sort of velocity. It's just going to go to that point and stop and just drop. There's no way it can go past through that, because all the energy is going to be transformed into gravitational potential energy, right, at 4r, the same height at point C, but there's no kinetic energy there. There's like plus k. There is no k. We use up all the gravitational potential energy. Okay, so briefly explain why this claim is incorrect. At point A, the block has a height of 4r, which has a UG of mg4r. At point C, the block will also have a gravitational potential energy of mg4r. Therefore, there is no possible way to have any kinetic energy at point C, and thus no velocity at point C. Therefore, the block will lose contact of the track and the track. Sweet. Okay. Now we're on question 2. Okay, we're flying through these frqs right now. Here we go. So I'm given a student hangs the spring of unknown spring constant K vertically by attaching one end to a stand as shown in figure 1. The other end of the spring has a small loop from which the small cylinders can be hung. In addition to the spring, the student has access only to the variety of cylinders. So tired. Oh my goodness. So I'm basically giving the spring, I'm giving unknown masses, and I'm also giving a scale and a stopwatch. So I need design an experimental procedure the student can use to determine the spring constant K of the spring. Okay, so I'm not gonna lie, I have looked at this problem before, but what I can say is that I'm thinking right now of an equation. My thought process right now, I'm thinking of an equation that I can use to be able to, because when I first thought of this, right, okay, I'll get back to my point later, my initial point later. When I first thought about this, I said, okay, maybe I can measure the height at which the spring is stretched, because I'm thinking of a spring potential energy, 1/2 kx squared, or something like that. But no, that won't work because there's no way that I can put mass in there. So I was thinking, okay, I'm given a stopwatch, right? And I have to use a stopwatch somehow. And so I thought, okay, when I hang it, it's gonna drop and it's gonna oscillate, right? And so if it oscillates, that means that's probably a simple harmonic motion equation, right? So I was thinking, okay, simple harmonic motion is Ts equals 2 pi rad m over k. And I thought, wow, this is actually everything I needed, because look, I'm giving it a time, which I can measure from the stopwatch. I'm also given a mass, an m, in the equation as well that I can measure from the scale, and I'm also given the thing I need to solve for, which is k, my spring constant, right? And so I was like, bet. So my procedure is that I'm going to measure all the masses, find out how much each of these cylinders weigh, right? And then I'm going to hang one of them, each one of them, on the spring, release them. When I release them, I'm going to start the timer right when it drops down, and right when it goes back up, I'm going to start the timer. It's going to go back up, and then I'm going to stop the timer when it gets back down to this minimum point again. That's going to be 1 period. That's going to be my TS. There I'm going to get a K, and then I'm going to do that with a bunch of different masses. Then I'm going to have a bunch of different variables for K. Right. Which should be good to go, I think. Yeah. Quantity be measured. TS, a symbol for quantity. What is this? This is gonna be the period for oscillation. Period of oscillation. Digital scale is gonna be what is the quantity to measure? The period of period of oscillation. What is the quantity to measure for the scale? It's gonna be mass. The cylinders. I think those are the only two things we need to measure. Yeah. Procedure diagram if needed. Find number 1. Find mass of each cylinder by using the digital scale. Hang one cylinder and hold it up, right? And then I'm going to release cylinder, allowing it to fall. While it's still shoot. Hang one cylinder on the on the what is it called? On the spring. Start stopwatch. The moment the block switches direction, as it's about to go up, and stopwatch when the cylinder reaches the same point. Minimum. Again. Sick. All right. Sick. Okay, then indicate the quantities. Did I do this right? Let's see. And then repeat with each cylinder. Six. Okay, B1. Indicate the quantities that could be plotted to produce a linear graph whose slope can be used to determine the spring constant K of the spring. So what I'm thinking about plotting it on the X on a graph, right? What's going on here? I'm thinking about what is my dependent variable and what is my independent variable, right? And so, for my independent variable, I can change the masses of the block, but I can also change the masses. Oh no, that's my independent variable. My independent variable is me changing the masses of the block. My dependent variable is the thing I'm measuring, and that's the time. So, if I think about it on a graph, my independent variable is going to be on the x-axis. So the x-axis is going to be weight, and then my y-axis is going to be time, and then the slope is going to give me the k. So what I can do is I can just use that spring. I can use the equation from up here and then isolate it until y equals, knowing that indomitable human spirit versus two full physics frqs. Who will win? I can solve this for the y equals, and my y-axis is gonna be my time. So I have to solve it for time. Oh shit, wait, is that already it? Time, and then my x-axis has to be weight. Oops, where'd it go? What? Yeah, independent variables mean mass. And TS has to be okay. So I need to get this m out of this square root. TS equals 2 pi, because I need to make sure that the slope has to be something related to k. So we rad m over rad k. TS equals so y equals mx, right? And then y is gonna be my time for my oscillate. Because when I think of independent variable, I think of y, but no, y is actually my dependent variable. Dependent variable is in time, so that's already there. 2 pi rad m, 2 pi over rad k times rad m. Okay, this is gonna be the equation to be used. Because, right, look, if I do this y equals mx type of thing, I have my x-axis, which is my independent variable, right? X-axis is going to be my independent variable because that's the thing I can change. That's the weight I can change. And then my dependent variable is going to be my time. That's the thing I'm measuring. And that's going to be my y-axis. So boom, boom, boom. So my slope will be this quantity right here. I can just manipulate whatever the slope I get to find my m, which is going to be my k. Okay, So that makes sense. My horizontal axis is going to be the weight, mass of cylinder. And then my vertical axis is going to be time, period of oscillation. Okay, here we go. We will describe how the slope of the graph will be analyzed to determine the spring constant K of the spring. Oh. We will describe how the slope of the graph will be used to analyze the slope of the graph will be 2 pi over rad k. I can divide the slope by how am I gonna see this into K, bro? How am I gonna K? What? By 2K, by 2 pi. And then multiply wait, if it was like 2K, I just have to do is divide by 2, right? Times a half. No, you don't have to do this to both sides, right? No, I don't have to. So I can just do times, divide by 2, AK. What? Am I crashing out? I don't understand this. Why does this not work? Huh. Why doesn't this work? I was gonna do T times rad M. slope equals 2 pi over k. So do rad k equals 2 pi over slope, and then square both sides. So k equals 2 pi over slope squared. Plotting the mass of the function of the period, mass of the function of the period squared will result. So plotting the mass square root will result in a slope used to find k by using an equation from the time oscillation equation, something like that. The equation of the period of an oscillating cylinder spring. Sick. Question 2. Oh, we're still on question 2. Oh my goodness. Different experiment. The student attaches one end of the spring to a force sensor attached to a wall. The other end of the spring, force sensor motion detector. Okay, this is actually stuff I haven't read before, so this is my first experience to look at them. Force sensor is attached to a wall. The other end of a spring is attached to a cart with mass m equals 0.25. Okay, 0.25. The student places a small motion sensor to the right of the cart, pulls the cart right at a small distance, so the spring is stretched to makes the cart from rest. Cart spring system oscillates. The velocity of the cart and the force F exerted on the cart as a spring. A function of time. Okay. Law of force. Equilibrium. Small force. That at equilibrium, no force can be the highest velocity. C. Using the data table from the velocity time graph, calculate the changing kinetic energy of the cart from time t equals 0.5 to time t equals 2. Shorter steps and substitutions. So this is at the period equilibrium. That's the highest speed. And then it's gonna go stretched, pull, boom, boom, stopped, equilibrium, so stretched, equilibrium, left, equilibrium. Right. So this one's being stretched. First subsection, and so at this point it's going to be stretched to the right. It's going to have 0 kinetic energy at point time t equals 0k. That t equals 0.5, it's going to have 1/2 mv squared. What's the mass? 0.25? V squared? What's V? 0.3. 0.3 squared is going to be 0.09. Okay, so it's going to be times t equals 0.5. So it's going to be 0 minus this whole value. I think. Could be wrong, but you know. Okay, 0.25 times 0.09 equals divided by 2. So 0 minus that, so it's going to be minus 0.01125 kilograms meter per second squared. Joules? Okay. Looks like it. Then C2. Using the data in this force time graph, estimate the change in momentum of the car from t equals 0.5 seconds to t equals 2.5 seconds. Of course, the change in momentum, momentum is P equals mv of the car from t equals 0.5 seconds to t equals 2.5 seconds. So 0.5 to 2.5. Right. Force time graph. P equals mv. So a lot of force, no force equilibrium. Oh, I have to use one of these equations, don't I? momentum. P equals mv, P. P equals fv, instantaneous. This is good. Fv cosine theta. So the velocity is the same direction as the force. Oh, okay. F net equals delta P over delta T. That's probably what I need to use. Change of momentum. This is a change of momentum. So delta P equals F net delta T. And I have F net here. So the change in force is 0. Times 2 seconds equals 0. So change of momentum equals 0 because the force, net force. Wait, hold on. Maybe. No, it's alright. Is 0. I think. Yeah. I wouldn't get this point though, but whatever. I think it just says that like the area under a force time graph is J. Area under a force time graph is delta P area under curve from 0.5 to 2.5 is 0. Okay. Do the data from the velocity time graph. Does the data from the velocity time graph confirm your estimation from the part C2? MV over T. T. Probably yes, right? I would say yes, cause yes, because how does energy relate to force? Yes, because kinetic energy is yes, because kinetic energy is related to force. Huh. Let me get some water. How many more questions I have here, bro? Oh my gosh, there's so many more questions. Oh wait, that makes sense. At t equals 0.5 and t equals 2.5, the velocity is velocity is 0.3 meters per second. Velocity doesn't change. And since momentum is velocity times time, since velocity doesn't change, then momentum this is consistent with my answer to part C2. Okay, I want to give up right now. Question 2. Because I am tired, low key, and I want to go work out as well. So, I'll be back. I failed. Whatever. I failed. We'll be back. Trust. Till next time.